What's up, YouTube? I'm going to run through a past paper attempt here. This is going to be section 2. So in my previous videos, I run through for this exact question, section 1, which included a couple of concept schemes. Now I've selected a concept scheme, and section 2, they're pretty much all the same on these past papers in terms of running through some design calculations, including some embodied carbon calcs, which I'll share, how I've approached that, and then presented some drawings and a detailed method statement. Just a note, I finally actually signed up to sit the exam. It's pretty expensive, so I beg you all, if there's anything here that you disagree with or you think is wrong, please let me know, because yeah, I'd obviously ideally like to just pay to sit this exam once. So here are the two concepts that I shared on my previous video. So I went with concept 2 on the basis that it was a sustainably superior design. When I say that, it should have less embodied carbon than my previous concept, or concept 1, and I won't go through that in too much detail. So section 2 starts with structural calculations, and I think the first part of that is we don't need to design everything. We're just going to pick the critical members. So as you can see, what I've identified here is I've got my CLT floor plates, I got my secondary glulam beams, I got my primary beams, I got my lift shaft. I don't know if a 600 UB even exists. I think it's a 610 UB. I got a lift shaft, I've got my columns, identified a transfer and some footing calculations, and then as the question requests, some embodied carbon calculations. So this is essentially like you would in any sort of computation package. You've got like a bit of an appendix going on here. Then the CLT floor plate, all the design guides that I've looked at, it talks about deflection and acoustics and fire really governing the design. So I've only really managed to find, I personally on a project haven't designed CLT before, so I'm actually not super experienced in it, to be honest. I've just found this sort of span table. I would hope to sort of like flesh this out a bit more, because I think it's a little bit crude for detailed calculations. However, yeah, I'm sharing what I've got at the moment. At the moment, yeah, I've got a span table which essentially shows how far my CLT spans, the load, and yeah, a little graph that I might sketch up in the exam to show that it passes, as well as some commentary around the fact that I'm aware vibration for these lightweight structures often govern, and maybe, yeah, just some notes on requirements around durability in terms of, avoiding any water ingress. What else do you have to worry about with CLT? We've got the vibration in there, and yeah, maybe some details around fire strategy and acoustics. Anyway, I wouldn't go too detailed, but just little commentary noting that this stuff needs to be accounted for in your design. Anyway, so span table, that's my CLT floor plate design. Glulam beam, going back to the basics here a little bit. Well, not the basics, just the fundamentals, I'd say. So my glulam beam, if you remember, these orange beams here, they're my secondary beams, and I'm really just showing they're a continuous beam. There's a bending moment diagram, shear force diagram based on the loading. What I am missing here, and I think I would put it somewhere in here, just talk about the standards that I'm using. So 1170.1 AS 4100, AS 3600. So they're the just design standards in terms of material standards and the loading combinations. Yeah, I think that's something. I'm in Australia, so that's what I would write here, which is essentially where I got my load combination factors. So my glulam beam, here I'm just doing essentially, I'm showing my calculations, I'm showing the design actions. You've also got my bending moment, the shear force as it spans over the primary beam or through the primary beam. And yeah, just some basic principles in terms of the bending and shear capacity. I think I've noticed here if we take a look at the loading criteria, one thing on this exam that like caught me out a little bit when I was doing the calculations, you can see on the plant room which is up here. It's got 7.5 kPa imposed loading. When I went to do my calculations, some of my members up there were failing, so I've just put this note in some of my calcs. It's a little bit fast and loose, saying, like here, for instance, I've got a bending capacity of 530, but the demand 600, so obviously that fails. But I acknowledge it's really just failing because I've got this high imposed loading just on my plant room here. So that's where I think I write something along the lines of, yeah, upsize my beams for bending in the plant room, but then in these other general floors, you can just stick to the beams that I'd used off my concept, which is based off just general span to depth ratios. So they're my glulam beams. I've got my 600 or 16 UB standard steel section. Again, same thing. So my UBs are these red primary beams here that I've got in my concept design. So yeah, they're just point loads that are dropping off my secondary beams onto my primary beams. So I think with the calculations, I'm trying to pull back on just like, endless calculations, because I know that it's a person that's going to be reading, and it's a lot more eligible to someone to understand your design if you can sort of illustrate it with some sketches. So that's what I'm really intending to do. Have like, some basic calculations, but also these bending moment and shear diagrams, which really illustrate my understanding of the design, the design of the beams and the load path. How's the load getting from the secondary beams back to the supports, and that's what I am intending to do with these shear and bending moment diagrams. The lift shaft, so this, in my opinion, the lift shaft is what I've identified over in my concept on the right hand side here as my lateral stability system. So that is why this wind loading that we get in the imposed loading, that's, in my opinion, where that comes into play. Where does it talk about wind loading? Here, 40 meters per second. So if you remember from university, 1/2 rho v squared to get your pressure. And then again, I'd probably go back up to my assumptions, or maybe write it here, the wind code that I'm using to actually get these more refined calculations where I've got like, my net pressure coefficient. And then I pick the longest or the widest elevation as my critical wind direction. Then I just quite crudely say, we're not using, this is just all hand calculations. Obviously, if you're using an analytical model, it would be a lot more accurate than this. But I've essentially said this hatching here is the width of the elevation that this core is going to pick up for wind in this direction. And then it's 1, 2, 3, 4, 5, 6. They're the sort of the frames that will take the load in this direction. So what I'm illustrating here is that this is the sort of the tributary width that this frame here is going to pick up, and it's shared between this frame and this frame. So I sketch that. Here's one frame essentially over here, and if you follow my calcs through, that's where I get, this wind pressure, which starts at 40 meters per second. I convert that to pressure, net pressure coefficient, blah blah blah. I get this UDL along the frame, and I essentially just turn that, it's a cantilever, WL squared on 2. You get a push-pull. These are all the same section sizes. I got 200 by 10 SHS, which is square hollow section. This is my critical section here because, it's in compression. And then I check the compression capacity for that effective length and get that. And yeah, I can tell that my member's okay. I don't worry too much about combined bending and compression in this because it's braced. So yeah, these diagonals are essentially taking the lateral load, and the verticals are taking the compression and tension. Then I've got a column calculation where I'm essentially, just sort of like as you would, doing a column load rundown, maximum force on my columns down here. It's not a moment frame, so again, quite crudely I'm just checking it for compression as opposed to combined actions. this is the capacity of my column when I take into account the effective length. Yeah, so my column's okay, great, let's move on. And then, yeah, I think it's really important in your calculations to identify any unique elements that are part of this design. And if I come over to the right hand side, if you remember in the question somewhere in here, it tells you about you can only have like a certain amount of columns on the roof. Does it say only 6 columns somewhere? Somewhere in here it says you can only have, yeah, there it is, there must be no more than 6 columns. So as a result of that, your columns essentially can't run all the way down as they do in the lower level. So that means sort of here in my concept there's going to be a transfer. As you can see, my roof framing plan has a column there, but it doesn't run through. So it's those critical elements that, yeah, I think are important to flag in your calculations, because that's obviously going to be a critical part of the design. So here I'm just showing, like, really simple. I worked out what the load on this column here based on the loads that they've given and the tributary of this column, and then I just do a simple PL on 4, and the 700 WB will be acting as my transfer in that location, and it, yeah, works fine. Perhaps it's a bit of an overkill. Then I get into my footing calculations. Now, yeah, with all of these calculations, I know there are more things to do, but I'm essentially trying to do the bare minimum to get it over the line. So in my opinion, a footing that isn't subject to uplift, even though maybe, yeah, a footing that isn't subject to uplift, I'm looking at bearing pressure and plunging shear. So that's what this calc here is. And I've separated it up for the bearing pressure. I'm using allowable bearing pressures, which is a service load. For punching shear, I'm highlighting that, okay, I factor it up by 1.5 or whatever design standard you're using for ultimate loads, and that's where I get my ultimate load, which is what I'm using to check for punching shear. One thing that I've done, and I think it's alright, like I originally had this sized at 600, which might be in the calc somewhere, and then I saw it failed, so I sized it up to 800, and then it passed. I wouldn't be too worried if you do that in the exam, because it's like, just cross it out and write what you're doing, because that is literally just a normal part of everyday design. Now, the embodied carbon calculations, I kind of cheated a little bit here, because I actually did my drawings in Tekla, because I just personally want to get better at it. It by no way will really help me prepare for the exam. But I do think it's a little backwards that the exam is testing you to draw by hand, because that's a bit archaic and no one's ever doing that. So to do your embodied carbon calculations, I think just identify the critical elements. So here I've got my steel sections, concrete, which is essentially the slab on ground, the footings, my CLT floor plates and the glulam beams. So after you identify the main structural elements, you have to pretty much estimate their quantity. So the quantity, I've kind of tried to get it all in kilograms, and again I've cheated a little bit here because I pretty much exported this out of a program, so I'm not going to be able to do that in the IstructE exam, so that's not the best prep, but this is the process that I'll be doing. Identify the elements, work out the quantity, times them by an embodied carbon factor. Now, the embodied carbon factor, IstructE has this whole sort of PDF which gives you some estimates, which is essentially where I got here. So you can see in situ concrete over here, I think that's where I got the 0.18. Where did I get that from? I think I've rounded this number here up. It's precast, maybe not the best number. Steel sections 1.74, concrete, steel, yeah, it's that number there, UK rolled open sections. So then you times your unit by the embodied carbon factor to get your total embodied carbon. That number here doesn't actually mean anything to me, so I tried to report it as a proportion. This guide, it would be better if it actually told you what the units is. So I understand it's kilogram of carbon dioxide equivalent per kilogram of whatever material. So for instance, for steel, I worked out I had this many kgs of steel, which is like 161 ton. Then I multiplied it by the embodied carbon factor, which I got from this table here. And then that gave me my total embodied carbon, which is obviously kilograms of carbon dioxide equivalent. And then I just, whether you don't really have to do it, but I thought it was quite nice just to show it as a proportion of your total embodied carbon. Now next is to put some drawings together. So here I start with a foundation plan where I just draw my foundations. I got my lift pits here. What I'm kind of missing is some schedules, so I think it would be nice if you just, wrote F1 and put that on all of your footings, etc. And then here you go to F1, you could write 3500 by 3500, just as you would in a normal footing schedule. So that's something that I'm kind of missing off my drawing here, but I've got a foundation plan. I've got my plan at level 1. Then at level 2, where you got the opening, where I've had to make some modifications to my glulam beams. Again, I have my member schedule here. This is all to scale. Level 3, which is that slightly, if we come, where is it? Level 3 has that, the plant room with the higher imposed loading. So because of that, what came out of the calculations, I've got some larger members in there to accommodate that, which would be illustrated here in my member schedule. And then my plant, my roof framing plan at the plant. This is slightly different to my concept sketch. I'm still using the lift frames here for my lateral stability, so I've added some diagonals at the top of my lift framing plan here, and I've just tied it in there and there, which gives me lateral stability in both directions, and I've just chucked in some roof bracing into that framing plan. And then some elevations, elevation on grid 1, elevation grid A, member schedule. Maybe one thing that I'm missing here is a detail, so maybe how I connect those secondary glulam beams into my primary 610 UB steel beams. That would be nice if I added that here, and potentially just that transfer member. But other than that, I think that's I'm going to be struggling with time to do anything more than that. And also I do know, I've just been using Tackler because I want to get better at it. But it doesn't really help me to prepare for the actual IstructE exam. Then finally, the last thing that asks us to do here in section 2 is to prepare a detailed method statement for the safe construction of the works. If you think I missed anything here, again, just chuck it in the comments. Be good learning for myself and anyone else out there. So I've got site establishment. What did I pull up? So site establishment, I don't know if you're going to get any, every site needs to do that, but it's not really specific. I've read a few of the examiner reports, and they want you to, understand the actual unique problems for this project, and don't try to avoid just being a generic thing here that can be copied and pasted anywhere. Anyway, in saying that, I've been a bit generic. I've got site establishment, then I've got detailed excavation and proof rolls, so that'll get me down to the soft clay layer that we identified in my foundations. One thing that's a little bit different that I changed: before I had a varying profile for the ground, but now I have decided to essentially excavate down to one layer and then fill the rest with mass concrete, which can be done. And it just means, we don't have to excavate down so much, and people aren't getting into deep excavations to pour your pad footings. So essentially, this is the stiff clay layer, and then from here to here I've got mass concrete, which transfers the load from my pad down into that stiff clay layer. So that is essentially what I'm saying in point 3 here. Then I pour my footings I've identified this this lift bit here can be precast, so I'm going to lift that in. As one precast unit. Pour my slab on ground. Install my columns, steel beams, then my secondary glulam beams, then I'll store my CLT floor. One thing with CLT, as we kind of mentioned before, and I put it in here, that it needs to be waterproofed until it is completely covered. So I've just added that in my method statement. Then I've got my plant roof framing. Then finally the things us as structural engineers, we don't get too caught up in the details of, but obviously the building needs to be clad and then finished off with the internal services and finishes. So that's what I've got for section 2. If you got any comments, just leave them and I'll get back to you. Thanks.